All right. Okay. Sorry, I got mixed up. This class ends at 9:30, so we got 20 minutes, and that's fine. That's enough to give cover this last topic, which is on confidence intervals. Okay. So we talked about the central limit theorem. We talked about the sampling distribution, and these concepts from the sampling distribution and the central limit theorem are absolutely necessary. Okay, they form the foundation for everything we're going to do here forward. Okay, so you've got to understand those things. However, just knowing this thing in of itself, it's a little abstract that it doesn't really pertain to our daily lives so much. Okay, because I'm saying, okay, let's say somehow we know that 35% of Americans own cats, but will we ever know that? We would not. Okay. I would have to do a census of everybody in the United States and figure out how many own cats, and then I can get an actual percentage, okay? But the next day, the crazy cat lady died, and so the percentage has changed, okay? Or maybe a new crazy cat lady was born, okay? We don't know, okay? So we don't know the actual percentage of Americans who own cats at any given moment, okay? So, but the central limit theorem, these problems, they say somehow we know the population proportion is this, and if we know the population proportion is this, then what's the probability that a random sample gives us this proportion? Okay, and the truth is we don't know. I mean, the truth is we do these problems and we do that, but in reality, this population proportion, this 0.35, is generally unknown to us because we don't know what the entire population looks like at any given moment. On the other hand, with confidence intervals, we're going to do the opposite, okay? We're going to say, let's say, so now we're not talking about cats anymore, but let's say I want to know what percentage of Americans own dogs. Okay. So somehow I conduct a random survey, okay, again, somehow. Very difficult in real life, but somehow I conduct a random survey and I survey 100 people. 100 people, and I ask, do you own a dog? And let's say 38 of them say, I own a dog. Okay? So what proportion in my sample owns a dog? 38%. 38 divided by 100 gives me 38%. What does this tell me about the American people? So, does that mean 38% of Americans own dogs? Not necessarily, okay. Is it possible that 40% of Americans own dogs? Mm-hmm. Sure, okay, so I've taken a random sample, and in my random sample, 38% own dogs. And I want to know, does that mean 38% of Americans own dogs? Maybe, maybe not, okay? Could 40% of Americans own dogs? Sure. What about 35% of Americans? Could they own dogs? Okay. Could the true proportion of Americans that own dogs, could that number be 20%?
Possibly.
Possibly, okay. It seems a little unlikely, right? If the true proportion that owns dogs is 20%, it would seem really weird that somehow my sample gave me 38%, right? Okay.
If it was truly random.
Yeah, if it was a truly random sample. Could the proportion be 60%?
Unlikely.
It's unlikely. I mean, theoretically, it is possible that 60% of Americans own dogs, and theoretically, it is possible that I took a random sample of 100 people, and somehow only 38 of them owned dogs. That's possible, but it's extremely unlikely. Okay? In the same way, it's possible that I flip a coin 20 times and I get 19 heads and one tail. It's possible, but it's very unlikely, right? So, and the reason why it's unlikely, okay, something in our brain intuitively says it's unlikely, but mathematically we know it's unlikely because, why? because the sampling distribution follows the central limit theorem, which is a normal distribution, which says most numbers are close to the mean, and technically 68% are within 1 standard deviation of the mean, 95% are within 2 standard deviations of the mean, and 99.7% are within 3 standard deviations of the mean. That's what the normal distribution tells us. So, because of that, we can create something called a confidence interval. Okay? So this is how a confidence interval works. So a confidence interval is, we do not know what proportion in the population has a certain trait. So basically we do not know P. But we take a sample, we take a random sample, the details of the random sample, not important, but it's got to be a random sample. We take a random sample, this random sample gives us a sample proportion P hat. And because of our understanding of sampling distributions, we're counting on the fact that P hat is not very far from P. Counting on the sampling distribution, so if I see P hat 38% of my sample owns a dog, what I'm going to say is that because I saw 38% of my sample owning a dog, I'm going to go say, meh, alright, and it's really not a meh, but it's like, okay, well, give or take 5%, we'll say something between 33% and 43% of Americans own a dog. I could say I'm pretty confident that between 33% and 43% of Americans own dogs because my random sample showed me 38% of my sample own dogs. Does that make sense? Okay. But if someone says 33 to 43%, that's a huge spread. Okay. Can you tighten it up a little bit? And the answer is sure. I could say, okay, well, maybe we can narrow it down and say we'll only go up or down 3%. So then I'd say between 35 and 41% of Americans own dogs. But am I more or less confident about this zone? Less confident, right? Because I've narrowed it. I've made it a little bit more narrow, and so now I'm not so sure, okay? Because the true proportion of Americans who own dogs could very well be outside of that zone. So there's this balance between how wide or narrow your confidence interval is and how confident you want to be. If you want to be 100% confident, you can always just say what?
Between 0 and 100.
0 and 100%. If you want to be 100% confident, someone says, what percentage of Americans own dogs? And then you know, they put a gun to my head and they say, tell me. And I say, okay, well, you're not going to like the answer, but I'm absolutely sure it's between 0 and 100% of Americans own dogs, okay? But you know, I'd be 100% correct there, okay? But if you wanted something a little bit better, you've got to narrow it down, but you're trading off how confident you are in the answer, okay? So a confidence interval, in the center of our confidence interval, we're going to put what we observe as our sample proportion. This goes right in the middle of our confidence interval, right? That makes sense, because as far as we know, this is our best guess for the proportion of our population. We don't know if our sample gave us too many Americans that like dogs or too few. We don't know if 38% is too high or too low. So this goes right in the middle, okay? And I'm going to go up or down, and so this is a plus or minus. I'm going to go up or down a certain quantity, and this quantity is known as the margin of error, okay? But the margin of error consists of two pieces. One is the z, I'm going to call it z star, and the other is, and you multiply that by the standard error, okay? This thing is called the margin of error. So prior to, you know, the election yesterday for mayor, or like 10 people voted. So prior to that, you know, there were some polls, and they said, you know, who are you going to vote for? And they said, you know, based on the polls, you know, Eric Garcetti is taking, you know, 50% with a margin of error of 3% or something like that. Okay, that's what this thing is coming from. Okay, so they surveyed people and they got a certain number, and then they went up or down a margin of error. We can actually figure out where that margin of error comes from. Okay, the z, this thing is known as our critical value, and this is called our standard error. The standard error is almost exactly like the standard deviation of the sampling distribution. It's almost exactly like that. But there's this very important distinction. Tell me if you can identify what that distinction is.
P hat instead of P?
P hats instead of P. Okay? The standard error uses P hats instead of P. So make sure that whenever you create a confidence interval, you're using P hats, okay? Actually, you can't use P because you don't know P, right? But that's an important distinction. And don't get this mixed up. Don't use the standard error when you're doing central limit theorem problem or something like that, okay? So make sure you distinguish these two. This critical value, critical values for confidence intervals of proportions, okay? We're going to have confidence intervals for other things, but when it's coming to proportions, our critical values just follow certain sets, okay? So z star will equal 2.58 for a 99% confidence interval, okay? It's going to equal 1.96 for 95%. It's going to equal 1.645 for 90%, and 1.28 for 80%. So if you want to be more confident about your interval, you just make that number bigger. You just widen out your zone. I'm 99% confident that the proportion of Americans that own dogs is between, you know, 38% plus or minus 30%, okay? Between 8% and 68%, okay? If I make it really wide, I can be very confident. But if I shrink it down, I'm trading off some confidence, but I'm getting a more precise confidence interval. Okay, so with our last 5 minutes, let's do an example. We probably won't have time where you guys get to do the example on your own. But we'll do an example together in class, and this should get you on your way. Okay. so let's say we take a random sample of 100 Americans. Okay. 38 own a dog. Make a 90% confidence interval for the proportion of all Americans that own dogs. Okay, so notice that we're talking about a proportion for all Americans, not just the sample here. So my p hat is 38 over 100. This gives me 0.38. If it's a 90% confidence interval, what is my z star?
1.645.
1.645. And what is my standard error? Square root of 0.38 times 1 minus 0.38 divided by 100. So let's do this. 0.38 times 1 minus 0.38 divided by 100. Square root of that. Okay. So this thing turns out to be 0.0485. I'm going to multiply that by 1.645. So I have 0.38 plus or minus 1.645 times 0.0485. I have 0.38 plus or minus 0.0798. Okay, so that's pretty much 0.08, but okay. So on the low end, okay, so if I do 0.38 minus 0.0798, that gives me 0.3002. And if I do 0.38 plus 0.0798, that gives me 0.4598. Okay, so pretty much 30% and 46%, if I round off. If you're going to do any rounding, do it only at the very end. Otherwise, I'd say keep about 4 decimals throughout the process of your problem. All right. And then what I would say about this, so this is now my confidence interval. So my 90% confidence interval is from 30% to 46%. And I would say I am 90%, so just hang on for a second. I am 90% confident that the proportion of all Americans that own dogs excuse me, is between 30% and 46%. Okay, and that's it. That's it. If you take a bigger sample, your standard error shrinks because n is in the bottom. It's in the denominator. This quantity is going to shrink. So if you take a bigger sample, this number shrinks, so then your confidence interval gets more narrow. If you have a small sample, this standard error gets bigger, so then your confidence interval gets a lot wider. Okay, and if you want to be more precise, you got to make a wider confidence interval. If you're okay with being, if you want to be more confident, you got to make a wider confidence interval. If you're okay with trading off some confidence to make a narrow confidence interval, that's there. Okay, so with that, we'll end there. So again, next week, homework for chapters 6 and 7 are due. You can choose to do the problems that he assigned, or you can choose to go to my website and do the problems that I've assigned and look at the homework solutions that I've recorded there. All right, we'll see you guys next week.